I'm Yang Liu. I'm a PhD student from North Carolina State University. Today, I will present a joint work among several institutes. My advisor, Xiaosong, is currently at Qatar Computing Research Institute, and the other two co-authors, Raghul and Sudharshan, they are from Oak Ridge National Lab. So this session is real systems, and the real system we target are the high-end computing system, like Titan at Oak Ridge Leadership Computing Facility. Titan is the second fastest supercomputer with a peak performance of 27 petaflops. It's a hybrid system with over 18,000 computer nodes. Currently, there are more than 400 scientific users who use Titan to solve the problem in areas like climate, energy, and some fundamental science. So, for enabling science on HPC, we are not only required enormous computational power, but we also required a massively parallel system. At ORNL, we have Spider. It's a Lustre-based file system, which provides an aggregate bandwidth of 1 terabytes per second and a total capacity of 32 petabytes. And on Spider system, we have multiple file system partitions. We call it VIDO. Each VIDO will have dozens of storage servers with dozens of DDN controllers, and as well as thousands of disks. So, although we updated to a faster file system, the I/O contention continues problem on the HPC domain. This is because large-scale systems like Titan, they are heavily shared resources. Multiple users are running at the same time and accessing the system, file system simultaneously. The resources like processor, memory, they are the only dedicated resource. The resources like interconnect networks and the I/O subsystem, they are the shared resources, which result in I/O contention, which cause a longer and highly variable runtime. It has affect the scientific productivity. It reduces resource utilization. So how to solve the I/O contention problem has attracted lots of research effort, especially in the HPC domain. One solution is to build smarter system software tools which could understand the application's I/O behavior and to make wise decisions. For example, with the knowledge of applications' I/O behavior, we can schedule the right group of application to minimum the I/O interference. Or we can suggest the application when to do checkpointing based on the current workload. To build such intelligence, we need to monitor and characterize the application's I/O behavior on a continuous basis. So in this work, we present a tool called I/O signature identifier. It performs this without interfering with the application I/O and no effort from the user. Next, for the rest of the talk, I will focus on the design and evaluation of our work. And first, before that, I will briefly surfing the existing method for client-side tracing. And I will first do the problem definition. Traditionally, the client-side tracing, such I/O information are collected with the client-side tracing, where the application's code is instrumented with the trace library. Client-side tracing is very useful during the development and debugging phase. However, for using such tools, there is a considerable development effort. And it is totally elective and voluntary for user to use such tool, so it's kind of tricky to perform a system-wide monitoring. What's more is there is a considerable performance overhead. Typically, it's 2 to 8%. What's more, different applications may have to use different I/O tracing tools, generate totally different trace format. Finally, detailed tracing will generate the large files themselves, which will bring extra workloads to the system. So for all those reasons, we think client-side tracing is not a viable solution on a continuous basis. especially for the large-scale system. So how about the server-side tracing, which is done by the system administrator rather than the user? Client-side, server-side tracing can collect the detailed information for IO pattern analysis, and also no user effort are required. However, we found the server-side tracing, they have a significant performance degradation and huge data generated. Here we introduce a different way for conducting the server-side IO characterization. Nowadays, the IO hardware, like a read controller, they often come with the cross-granular logging capability. Like the DDN controller used on Spider, they will automatically record the average bandwidth each second. And the Spider has been using a tool to query such information in a 2-second interval, and save those information to a database. Those information are collected almost zero overhead, and there are no impact on the user I/O, and there is no user effort is required. Here, this plot shows the history throughput logs on Spider system for a typical day. The problem is all the information, all the IO traffic information we get are mixed throughput information from all the concurrent workload. So this work, we study how to mine those aggregated time series data and figure out what the IO intensive application may be doing. There are several, we rely on several inherent features of scientific application to solve our problem. Typically, the scientific simulation, they have a computer phase, and they will do computation for a fixed number of time steps, and then they will go through the IO phase and to write out the intermediate results and the checkpoints. So this results in two very important features or assumptions used in our work. The parallel scientific application, they generate bursty traffic and with a relatively regular periodic pattern. Also, it is recognized that the scientific application, they tend to be repeated multiple times with the same input or segment configuration, system configuration. Finally, another problem is we focus on the big IO consumer in this work whose IO traffic are visible among all the concurrent workload. So this is our research contribution, a tool called IO signature identifier, IOSI, for identifying the IO signature of the target application. First, given the target application, we look into the Titan's production job scheduler logs, and we find out the execution history. And with those start time and end time pairs, we look into the Spider server-side throughput logs, and we cut off the relative segment of the server-side throughput logs. And each of such segment, we call it a sample. And here is another important definition, is the IO signature. The IO signature here is the IO throughput observed at the server side. In other words, for example, we run this target application alone on the system, and the IO throughput information we observed on the server side is the IO signature of this application. And another definition is the burst. It is a period of elevated IO activity. We call it a burst. And usually the IO signature is composed of multiple bursts. So IOC is simply like this. Commonality across multiple samples tend to belong to the target application's IO signature. Through our design and evaluation, we will use multiple pseudo-applications generated by a parallel benchmark called IOR. And here is the L signature of one pseudo application, and there are 5 samples of this pseudo application. The signature we captured is during the Titan's maintenance window, so the spider file system is almost silent. Extracting the common feature from the noisy samples is a challenging task. And the first problem we met is the background noise. We can see during different samples, the background noise, they are totally random and unpredictable. Sometimes even the whole sample are dominated by the noise. Another thing we observe is the noise will not only superimpose on the target burst, they will also distort the L activity of the target application. And we show an example here. There are 2 samples in red and blue color. And in this area, we can see the blue sample gets slowed down. So the second and the third burst of this blue sample, it gets delayed. And we call it L drift. By considering all those problems in processing multiple samples, we met this interesting dilemma. The common burst is the only thing we can align the samples, but we need the properly aligned sample to find out the common burst in the first place. And next, we will solve those challenges with IOSI. And internally, IOSI uses those 3 steps and to find out to extract the final L signature of the target application. The first stage is data preprocessing, which make a huge difference on our experience. There are totally 4 steps. The first step is outlier elimination, which is tries to find out the sample with much higher noise or with abnormal execution time. Here we show 5 samples, and which is the bad sample is obvious, right? This one, it has much noise than the others, than the majority. So we applied an existing tool called local outlier factor to identify and remove such outliers. Next, we perform 2 steps related to adjusting tempo dimension. The first is we noticed that L burst sometimes only lasts for a few seconds. And so we adjust the time, we adjust the time from 2 seconds to 1 second by using this linear interpolation. Next, we remember that we mentioned the contention will create drifts and will cause a sample with different durations. And here we show 4 samples, and they have a different execution time. But the difference should be minor here because we already removed the outliers. And one observation is noise will make the sample slower, and so here the shortest sample should be closest to the true L signature, and we normalize the samples according to the shortest one, and by discarding the data points with a regular interval. And here the result after we do this duration correction. And the last step of data processing is to deal with the routine background noise, which indicates the light activity generated by the interactive usage or regular maintenance tasks. And here we applied a 2-level filtering to perform this. For this 2-level filtering, the first step is we calculate the mean value of all the whole samples, and we collect all the data points lower than this mean value, and we calculate the mean value for the collected data again, and we use this value to lower all the data in the original sample. So after data pre-processing, we can see the outlier get removed, and the sample get finer granularity, and they have identical execution time, and they have a lower background noise. The next stage is per sample wavelet transform. Here we use wavelet transform is because we want to use burst as basic unit of the signature identification. And we want to first isolate those individual bursts from the background or from each other. But sometimes it's difficult when the bursts they are very close to each other or they're overlapping with each other. Like this, in this area, it's not obvious to draw the boundary for this burst. So we use wavelet transform is a tool which can be used to remove the white noise or smooth the sample. And we have more details in our paper, and here I just show the after picture. For this wavelet transformed sample segment, we can see it's much easier to identify the burst as the area between two adjacent low points. So next stage, we will perform this cross-sample L burst identification through density-based clustering. And we adopted an existing clustering approach called Clique. Here, first we map all the original sample to a new 2D clustering space. In the 2D clustering space, each point represents a burst in the original sample. And the x value of this point is the time corresponding to the peak of the burst. And the y value is the relative similarity. It is between this burst and a reference burst. It's calculated by correlation coefficient, which measures the strength of the linear relationship between two sequences. So due to this transitive nature of this measurement, the similar L burst, they will be close to it. They will have a close similarity to this common reference burst. And we show after we map all those 4 samples to a single clustering space, you can see if those points from all samples they are close to each other, they are likely from a common burst. So here's an example to show how this Clique clustering works. There are 4 samples represented by different bullet shapes. And the main idea is to find out the dense unit in which the number of samples is above the given threshold. And we can see in this central unit, it satisfies this requirement. And then we will extend the search to the neighboring area. And by using a higher threshold, we will try to see if this neighboring area is dense or not. And we see there are 4 samples. We find out the points from all those 4 samples in this neighborhood area, and it will be considered as dense. And we will find those time and shape information of those points from the original sample, and we will aggregate them and put it into the final extracted L signature. And we will repeat this until we find out all the L signature of this target application. Also, there is one problem is here we can see it's a high sensitive to the size of the unit, and we have more details in the paper about this. So for evaluation of this LC, we use 2 types of application. We use LR, which is a configurable L benchmark. We generate 3 write-intensive pseudo-applications, run it on Smoky. It's a development cluster. And we also use SVD. It's a real scientific application. It's a simulation solver. We write on Titan with 18,000 processes. So here, due to the time limits, I only show the IOSCD, the result of IOSCD. And here's the IO signature of IOSCD, and we're using the client-side tracing tool to get this signature. There are 7 samples, each with a different noise level. And here is the extracted IO signature by IOSI with data preprocessing. Unfortunately, we found out that there is one burst missing here, and we see this is due to incompleted throughput logs and due to the heavy noise on the last burst. In the accuracy comparison part, we compare our IOC with existing approach called dynamic time warping. It's a widely used alignment technique. And DTW will take 2 samples as input, and we will average the output. And repeat this process until all the samples are done. And from this, here we use cross correlation and correlation coefficient to measure the accuracy of IOC. And from those 2 figures, we can see IOC with data preprocessing outperforms the other 2 clearly. Also, we see IOC, they have cheaper, it's cheaper than the DTW, the time complexity. So to conclude, we found that it is possible and affordable to identify the individual IO-intensive applications' bandwidth demands by using the aggregate server-side throughput logs without interfering with the user I/O, and no user effort are required. And here we want to mention several interesting problems and want to discuss with the audience. If our tool can be applied, also can be applied to the commercial computing. Like we think, for example, we think it may be helpful to identify the individual VMs IO needs and to do some smart thing. But the key requirement here is those workloads should have a repeated IO pattern, and the workload should be visible during all the concurrent workload. For example, at least we think it can be applied to some example like MapReduce or something. But we have to, of course, we have to handle those extra challenges, such the complexity brought by caching, something. Oh, that's it. Thank you.
Hi, Kun Tan from Virginia Commonwealth University. Well, in your work, you extract the IO signature from the scientific simulation applications. And my question is, I'm wondering whether scientific simulation applications will run repetitively with a similar or even the same IO signatures to let you schedule.
Okay. You're asking if it's like they will run the scientific application multiple
multiple times.
Yeah,
with the
here
same
we from several previous studies and from our observation, we see it's true. The scientific application, they will be run multiple times, maybe with a different input, but they will run it with similar system configurations, like number of nodes. Here I have an example to show. So we observed that from our job history logs, we see those users, they will run the application multiple times with the same number of nodes on Titan system.
Okay,
And
thank you.
Hi, Raghul from UMN. Thanks for your talk. Assuming that I have this signature from your work, have you ever think how we can reproduce the same workload with the same signature without having access to those scientific applications? So my question is that if I have those signatures from your work, have you ever think how we can reproduce the same workload which has that kind of signatures?
Reproduce the same workload?
Yeah.
So you want to ask if we already have the signature. If we have the signature,
Yes.
will they reproduce the signature like in
Again, yeah.
again?
Yep.
Yeah, just like I said, because from multiple studies, we already see the scientific simulation, they will repeat their IO behavior like multiple times or in the future. And they always run those applications multiple times. That is the meaning of this work, right? We get those IO signature, we can use it in the future to do the resource allocation or scheduling.
I see. Okay, thank you.
Thank you.
All right. We could thank Yang one more time and the other speakers in this session.